Hi everybody, I'm Alan Cantle and I'm the OCP High Performance Compute SubProject technical lead. And in that subproject we're creating the High Performance Compute module, which we've called the HPCM. And today I specifically want to talk about the CXL enablement with this HPCM module. So my background in shared memory architectures, memory-centric architectures, goes back a long time. And in fact, previously, before CXL, when OpenCAPI was popular from IBM, I was the technical lead of the OpenCAPI consortium. And back in a couple of years ago, I actually prepared a presentation that concluded that this diagram was a nice generic domain-specific architecture template for creating future computing architectures. And you can very much see it's tiered memory centric, and it views computing from the cloud to the edge in the intelligent IoT. And one of the important things about this is it talks about the data plane continuum. And you can see the processors, different types of heterogeneous processors on the outside, but in an ideal world, every processor would have its local memory just next to its processor. And it's all relative. So for instance, this one up in the top corner would have its local memory, but this one could be in Australia where the other one's in the USA. So obviously what's near to one memory, to one processor, is actually far memory to the other processor, and vice versa. But this is really the way we're going to look at the future. And CXL is obviously, with memory pooling, is really driving this initiative. And I think this is going to become more and more of a shared memory architecture. So bearing this big picture in mind, let's zoom in a little bit more into what I would see as the ideal CXL architecture. And this is an abstract view right now. So firstly, we want to tightly couple compute with all memory types. So you take your high performance processor, all different heterogeneous processors and or switches, and you want to really be able to attach many terabytes of shared memory, ideally locally as possible. And that shared memory can include volatile memory, persistent memory, or even file system storage memory. And the key thing here is we would really want a nice local CXL memory interface. But as well as that, we want to be able to efficiently share that processor's memory, that processor's local memory, with other processors. And so we have a high bandwidth memory pooling data plane fabric where we can share those resources, those memory resources, to everyone else. And that's the CXL fabric interface. So if we take this simplistic model, it's a very simplistic building block, and we map it onto my big diagram, we can see that you've got your data plane continuum which has got the data plane fabric, and we've got the memory in the tiered memory structure and local to one processor. And when you think about it, we simply have to step and repeat that across all of the processors and memories. So we have a very simplistic and modular, fairly fine granular step and repeat architecture for building the future of computing architecture. And so what we're trying to do with the high performance compute module is we're trying to make a physical instantiation of this abstract view we're looking at here. So let's take a closer look at the HPCM. Firstly, it's a blind mate powered and liquid cooled module. And so it's a standalone module. It's roughly the size of an OAM module. In fact, it was inspired from the OAM, the OCP accelerator module. And you can see in this picture, it's got one of the big processors. It's just a cartoon of one. that can burn up to 1 kilowatt in power, depending on the processor. And also you can see a couple of pins there that are actually the BlindMate pins that will bring in the 48 volts to power this module. On the bottom side though, instead of like the OEM bit plugging in with mezzanine connectors to a motherboard, we've got a bunch of connectors that look more like a backplane. And what we have here is we've got 16 EDSFF connectors, the 4C and 4C plus connectors, that can support the E3.S formats, for example, or the NIC 3.0, etc. And on the edges, we also have 8 topology connectors. The sum total of all the transceivers and all of these connectors adds up to quite a significant 320 transceivers. If we actually populate the module with 16 E3.S media devices, it can be memory or storage or DRAM, persistent memory or volatile DRAM. You can see we've got a really good 3D module here. And one of the key features is everything's really tightly coupled, so you've got good signal integrity and potentially low energy for the data movement. And then we wrap all of that in a water-cooled infrastructure to cool everything with water and actually have a potential for energy recovery here. And these have got 4, you can see these 4 BlindMate water connectors. So we have BlindMate water and power. So this is essentially the building block that we're using that we can step and repeat to build heterogeneous computing architectures. Here's a diagram just to give you a feel for this is showing 8 modules, and it's giving you a feel for how the topology can be interconnected. And the cabling you see on the left, this was an OAI chassis example, but it's showing an all-to-all fully connected interconnect between the 8 modules, as well as expansion beyond those modules. And the diagram on the right is the same cable diagram, but populated with the E3.S modules and a few NIC 3.0 modules. So you can see how the topology is actually built up. So from a CXL enablement prototyping platform perspective, I've shown this little 4 high-performance compute module benchtop example. So you see 4 modules there on the right, populated with a total of 64 E3.S media modules. And if we look at that from a top-down and a side view, we can begin to map some examples. So let's just, in this example, I'm just showing the different types of HPCM modules that could actually be built based on different high power processors. So we're actually currently working on the AMD ACAP AI FPGA module, bringing that into reality. And we're also testing out the thermal and power infrastructure. That's one of the key first steps that we're working on today. But some of the early sites that we've got on additional modules to build would be the AMD MI300, the CPU GPU combo, the Intel Agilex CXL FPGAs as well, and also a startup called Fabrica that are building a CXL and Ethernet switch. And I've just given a few examples here of the different media types, like a Micron CXL.mem, or if you look at Samsung, they've got some really interesting products. They've got some smart SSDs where they're actually hybrid. They've got hybrid. It's a CXL.mem interface with like hybrid DRAM and SSDs built in. You can use ordinary standard NVMe SSDs from anybody, and also a CXL.mem example from Samsung there. So you would populate this with the type of memory and the capacity you actually required. The topology interconnections here, I'm just showing an example where you've got quite a lot of bandwidth. You want a high bandwidth maybe between the MI300 and the AMD ACAP FPGA. So you manually populate a lot of links between those two. But basically this is all cabled, so you can build any topology that your domain specific application needs. So that's the flexibility of this platform. So you can begin to see, in terms of interoperability testing with people's media devices or different accelerators in heterogeneous combinations of CXL devices, this provides a very low cost way on the benchtop for researchers to build and play with different CXL based architectures. Now there's a critical part of the actual module itself, and this is a huge thing which obviously the Composable Memory Systems Workgroup that this meeting is all about is really focused on, and that's the CXL fabric management. Obviously we need some level of BMC controller, a board management controller, to actually bring these modules. These modules will all need to be self-bootable, and we're going to need to be able to discover these, and that's again what CMS is all about. So one of the things that's been happening for a long time on the BMC front is we've had OpenBMC, which is fully open source software BMC, which has really made great strides now. But one of the bigger challenges, especially from a root of trust perspective, is the openness of everything in the BMC controller. And so they want to open up the hardware architectures as well that have traditionally been more proprietary. And so there is an activity that's been going on for a number of years called LibreBMC, where they're actually using basically blank canvas FPGAs, and then Lattice and Xilinx are the two participants in this effort to actually make the BMC controller, and then you layer in a soft way, soft processors or low-level hardware management, and that's all open sourced as well inside the FPGA. And so this diagram is showing that we've chosen Lattice for this approach, and we're using their ICE40 devices to really compress all of these sideband signals, which there are quite a few of them with all these interconnects, into this single wire aggregator. And also they're using LVDS tunneling protocol interface LTPI, which has been open sourced to OCP and adopted in the data center security module DCSCM as well. So we've got the basic hooks in here, and more work needs to be done. But this could be a wonderful exploratory platform for as we research the fabric management pieces of a CXL enabled computing architecture. So if we look at where this potentially could go, yes, we're talking about it for CXL enablement, but we have a vision that this can actually replace 19-inch racks in a data center with something that we're calling wall of compute. And in here you can see we've built a small wall where you've got 16 modules high, which is roughly the height of a 19-inch rack, and then we've got 8 modules wide in this small snippet of a wall. And as an example on the right, I've just shown you a couple of different types of potential heterogeneous HPCM modules that there could be with different color codes. And just to give you by way of example, if you take the current Frontier supercomputer with 4 GPU modules and 2 CPU modules, you could emulate a Frontier node, and you could wire the topology of that to be identical to Frontier. Likewise, if you really wanted to tightly couple a CPU with a GPU, something like NVIDIA have done with Grace Hopper, then you could have a lot of interconnect between these two modules and just tightly couple them together. Or if you wanted to build the previous supercomputer called the Summit node from IBM and NVIDIA, which is 2 CPUs and 6 GPUs in a node, we can do that. And again, that specific wiring can be easily configured. Or maybe you would like to build a GPT-3 optimized AI cluster where you've just got a bunch load of AI inference chips ganged together to perform really high performance GPT-3 implementations, ChatGPT, etc. Or maybe you just want to do a disaggregated FPGA pool. You can build that just with several modules. And finally, just as a bit of humor, you can literally mix anything to make a particular application run well. And I've just named it Burger King, have it your way. So hopefully that gives you an idea of the potential of where this could actually go. So in summary, CXL will fundamentally change computing architecture, and exactly how is still really a pathfinding exercise. HPCM allows for a highly flexible and a low-cost architectural exploration, which is really, we're still finding our way here. So that's what HPCM enables that. And I can certainly see that HPCM and CXL will democratize our industry at a pluggable system level, where we can mix and match heterogeneous processors from all of the different vendors and various startups. And finally, my hope is that the walls of compute with HPCM may actually revolutionize the data center itself. So thank you very much.